Welcome to the world of time and space complexity. These are super important ideas in computer science that help us figure out how fast a program runs and how much memory it needs. Don't worry if this sounds complicated. We're going to break it down into simple, beginner-friendly pieces with a fun real-life analogy to make it crystal clear. Imagine you're running a lemonade stand. You want to serve your customers quickly, that's time complexity, and make sure you don't need too many supplies or space to store them, that's space complexity. As more customers show up, you need to know how your serving speed and storage needs change. Time and space complexity help us predict this for computer programs, so we can choose the best way to solve a problem. Time complexity is about how fast you can serve lemonade to all end customers. If you take longer to serve each customer, or if the line gets super long, it affects how quickly you finish. Space complexity is about how many pitchers, cups, or lemons you need to keep the stand running. If you need more supplies for more customers, that's like using more memory in a program. By understanding time and space complexity, you can plan your lemonade stand or program to handle small or huge crowds efficiently. What are time and space complexity? Time complexity. This tells us how long a program takes to finish its job based on the amount of work it has to do. Instead of measuring time in seconds, we count the number of steps the program takes as the input size, called N, grows. For example, if you have more lemons to squeeze, it takes more time to make lemonade. Space complexity. This tells us how much memory or storage a program needs to do its job. This includes space for things like variables or lists, and it also depends on the input size N. Think of it like how many pitchers or cups you need to store your lemonade. Big O notation, the simple way to talk about complexity. We use something called Big O notation to describe how time or space complexity grows as the input size, N, gets bigger. Big O focuses on the worst-case scenario, the maximum time or space a program might need. It's like preparing for the busiest day at your lemonade stand, so you're ready for anything. Big O simplifies things by ignoring small details, like exact seconds or tiny amounts of memory, focusing on the big picture of how the program behaves when N is really large. Think of Big O as a label to your lemonade stand that says, "This is how busy it gets when tons of customers show up." For beginners, we'll focus on three common types of time and space complexity: O of 1, O of n, and O of n squared. Let's dive into each one with examples and our lemonade stand analogy. O of 1, constant time and space. O of 1 time complexity. What it means, the program takes the same amount of time no matter how many inputs, N, there are. It's super fast because the number of steps doesn't grow with N. Example, checking if you have enough sugar in your jar to make lemonade. You just look at the jar and see if it's full. Whether you're serving one customer or 100, it takes the same quick glance. Lemonade stand analogy, pouring a single glass of lemonade from a pitcher. No matter how many customers are in line, N, pouring one glass always takes the same time. Why it's great? O of 1 is the fastest possible time complexity because the work stays constant. O of 1 space complexity. What it means, the program uses the same amount of memory no matter how big N is. It only needs a fixed amount of space. Example, keeping track of how many lemons you have in a single notebook. You write down 10 lemons in one spot. Whether you're serving 1 or 100 customers, you only need that one notebook entry. Lemonade stand analogy, using one pitcher to hold lemonade. You don't need more pitchers just because more customers show up. Why it's great? O of 1 space means you're super efficient with memory, like running your stand with minimal supplies. O of n, linear time and space. O of n time complexity. What it means, the time it takes grows in proportion to n. If you double the number of inputs, N, the program takes twice as long. Example, counting how many customers are in line at your lemonade stand. You look at each customer one by one and count them. If there are 10 customers, you take 10 steps. If there are 20, you take 20 steps. Lemonade stand analogy, serving lemonade to each customer in line. For each customer, N, you pour one glass, so more customers mean more pouring time. Why it's okay? O of n is still pretty efficient for small or medium-sized inputs, but it can get slow if n is huge, like a line of 1,000 customers. O of n space complexity. What it means, the memory used grows in proportion to n. If n doubles, the memory needed doubles too. Example, writing down each customer's order in a notebook. For each customer, you write one order, for example, 1 lemonade. If there are 10 customers, you use 10 lines in the notebook. For 20 customers, you use 20 lines. Lemonade stand analogy, giving each customer their own cup. If you have n customers, you need n cups, so more customers mean more space for cups. Why it's okay. O of n space is manageable for small inputs, but it can be a problem if n is very large and memory is limited. O of n squared, quadratic time and space. O of n squared time complexity. What it means, the time it takes grows quadratically, meaning if you double n, the time increases by 4 times, n squared. This can get slow fast. Example, making sure every customer shakes hands with every other customer at your lemonade stand. Maybe it's a friendly community event. If you have 3 customers, each one shakes hands with the other 2, so you have 3 times 2 equals 6 handshakes. For 6 customers, it's 6 times 5 equals 30 handshakes. The work grows with n squared. Lemonade stand analogy, pairing every customer with every other customer to share lemonade samples. For n customers, you need n times n interactions, which takes a lot of time as n grows. Why it's slow? O of n squared is fine for small inputs, like 10 customers. But for large inputs, like 1,000 customers, it's way too slow because 1,000 squared equals 1 million steps. O of n squared space complexity. What it means, the memory used grows quadratically. If n doubles, the memory needed increases by 4 times. Example, creating a chart that tracks which customers have met each other. You make a grid where each row and column represents a customer, and you mark if they've met. For 3 customers, you need a 3 by 3 grid, 9 spaces. For 6 customers, you need a 6 by 6 grid, 36 spaces. Lemonade stand analogy, setting up a table with n rows and n columns to track customer interactions. For n customers, you need n times n spaces, which takes up a lot of room as n grows. Why it's a problem? O of n squared space can quickly use up all your memory for large n, like needing a giant table for 1,000 customers. Comparing O of 1, O of n, and O of n squared. Let's see how these complexities compare using our lemonade stand. Customers, n 10. O of 1 time, pour 1 glass 1 step. O of n time, serve each customer 10 steps. O of n squared time, customer handshakes 100 steps. Customers, n 20. O of 1 time, pour 1 glass 1 step. O of n time, serve each customer 20 steps. O of n squared time, customer handshakes 400 steps. Customers, n 100. O of 1 time, pour 1 glass 1 step. O of n time, serve each customer 100 steps. O of n squared time, customer handshakes 10,000 steps. O of 1, always fast, like pouring 1 glass. O of n, grows steadily, like serving each customer. O of n squared, grows super fast, like coordinating handshakes for everyone. For space, it's similar. O of 1, 1 pitcher, no matter how many customers. O of n, 1 cup per customer. O of n squared, a giant grid to track everyone's interactions. How to analyze time and space complexity. Here's a simple way to figure out complexity for beginners. For time complexity, look for loops. No loops, just 1 step, like checking a sugar jar. That's O of 1. 1 loop that goes through n items, like counting customers. That's O of n. 2 nested loops, like pairing every customer with every other. That's O of n squared. Focus on the worst case. What happens when n is really big? That's what Big O cares about. For space complexity, count memory used. Just a few variables, like 1 notebook. That's O of 1. A list that grows with n, like 1 cup per customer. That's O of n. A grid or table that's n by n, like tracking customer meetings. That's O of n squared. Include temporary storage. If your program needs extra space, like a temporary list, count that too. Common mistakes to avoid. Mixing up time and space. Time is about steps, speed, and space is about memory, storage. Keep them separate. Forgetting about big inputs. Complexity matters most when n is large, like a huge line of customers. overcomplicating. Just focus on the biggest part of the work. For example, if a program does n squared plus n steps, the n squared part is what matters, so it's O of n squared. Why this matters in real life. Understanding time and space complexity helps you write better programs, just like planning a great lemonade stand. Choosing the right approach. Use a fast O of 1 or O of n method instead of a slow O of n squared 1 for big tasks, like serving thousands of customers quickly. Making apps run smoothly. A slow program might freeze a game or website, but a fast one keeps users happy. Saving resources. Efficient programs use less memory, like running your stand without wasting supplies. Conclusion. Time and space complexity are like the rules for running a successful lemonade stand. Time complexity, O of 1, O of n squared, tells you how fast you can serve customers, and space complexity tells you how many supplies you need. By learning these ideas, you can predict how your programs will behave and choose the best way to solve problems. Start practicing with simple tasks like counting items, O of n, or checking a single value, O of 1, and you'll soon be a pro at making efficient programs. Keep experimenting and have fun building programs that run as smoothly as a perfect lemonade stand.